Hello, welcome to GP Podcast. Every single piece of modern tech that you use, your phone, your computer, all of it, is built on top of a microscopic city. It's a city built not with steel and concrete, but with light. And at the very heart of its construction, there's this hidden battle going on between human ingenuity and the fundamental laws of physics. Today, we're going to pull back the curtain on the digital mastermind that makes sure ingenuity wins every single time.
All right, to really get a handle on this, let's start with an analogy that just perfectly captures the insane scale we're talking about. I want you to stop thinking of a microchip as some flat little circuit. Instead, picture it as a dense, impossibly complex, tiny skyscraper. It's a vertical metropolis humming with logic and memory.
And when I say dense, I really mean it. Inside each one of these tiny skyscrapers, you'll find billions of transistors. Billions. These are like the individual rooms, the offices, the apartments of this microscopic city. I mean, that's a population count that rivals our entire planet, all crammed into a space smaller than your fingernail. It's just wild. And this skyscraper doesn't just spread out, it stretches up, way up. We're talking more than 100 distinct layers or floors. Now, here's the crucial part. Every single one of those floors and every one of those billions of rooms has to be wired together perfectly. If even one connection is faulty, the whole city just goes dark. So how in the world do you build something so complex, so unbelievably small? Well, you have to enter the nanometer scale. And this is a realm where the very laws of physics, the rules of our universe, start to fight back against you. The basic construction method is a process called lithography. To put it simply, you shine a very special kind of light through a blueprint. They call it a mask. That light then projects the pattern from the blueprint onto a silicon wafer. You're essentially printing the circuit design one painstaking layer at a time. And right there, that's the heart of the problem. See, when you're trying to make features that are just unimaginably small, light doesn't behave the way you want it to. It doesn't act like a perfect, sharp tool. It bends, it diffracts, it kind of blurs the edges. So the question becomes, how can you possibly draw a perfectly straight line when your pen is absolutely determined to wiggle? And you know, it's not just the light. At this tiny scale, it feels like everything is conspiring against you. The physics of the light, the chemistry of the silicon wafer, they all work together to deform the pattern you're trying to print. Your perfect blueprint ends up looking like a distorted mess, almost like you're seeing it in a funhouse mirror. For a long time, this was looking like a serious roadblock for technology. I mean, how do you defeat physics itself? Well, it turns out you don't. You outsmart it. And that brings us to the hero of our story, a digital mastermind that actually anticipates all that chaos and engineers perfection out of it. It's called computational lithography. And the solution here isn't to somehow force the light to be perfect. No, that's impossible. Instead, this system uses incredibly sophisticated software to predict exactly how the pattern is going to get messed up. It literally sees the distortion coming, and it makes corrections before it can even happen. So, how does this digital mastermind actually pull off this magic trick? Well, it uses this powerful three-step strategy to pre-correct every single potential error, making sure that the final result is absolutely flawless. These are the three main tools in its arsenal. You've got source optimization, mask optimization, and wavefront optimization. You can think of them as controlling the light source itself, the blueprint, and the actual path the light takes to get there. First up, the system takes a hard look at the light source. Using these incredibly complex calculations, it meticulously adjusts the shape and pattern of the light being used. By tailoring the light for the specific pattern it's trying to print, it can create a much sharper, much clearer image right from the get-go. Okay, next up is mask optimization. And this is where things get really clever. If the system knows that the light is going to bend the corners of a square, what does it do? It changes the blueprint. It actually designs a mask with these bizarre, distorted shapes that look nothing like the final pattern. But, and this is the genius part, they're precisely calculated so that when the light inevitably bends them, they land on the wafer as perfect squares. It's like writing a distorted message that only a funhouse mirror can read correctly. It's amazing. And finally, there's wavefront optimization. The super intense light used in this process creates a lot of heat. That heat can actually cause the lenses, the optics, to slightly change shape. Even a change of a single nanometer can ruin the whole chip. So this system reshapes the light in real time to counteract those tiny heat-induced deformations, making sure the light's path always stays true.
Now, what's truly mind-blowing isn't just that this process works. It's the relentless, unbelievable scale and speed at which it has to happen to make all the technology in our lives even possible.
I want you to really think about this. This entire three-step correction, this intense calculation and precompensation, it happens for every single pattern, on every single layer, for every single chip, on every single wafer. It is an almost unimaginable loop of perfection, repeated millions and millions of times, all happening at the lightning speed needed for mass production.
And the results of this digital mastermind's constant obsessive work? Every floor of that tiny skyscraper connects. Every single one of those billions of transistors can talk to its neighbor. The city functions. Your phone turns on. The entire modern world works.
But this battle against physics, it is far from over. As we all demand more power, more speed, more efficiency from our devices, these tiny skyscrapers have to get even taller. Their features have to shrink even further. And that means the physical challenges just become more and more extreme. The task only gets harder.
This whole thing really leaves us on the razor's edge of what is physically possible. As these tiny skyscrapers keep getting taller and their components shrink even further, the real question is, what's next? What new kind of mastermind will we need to invent to keep outsmarting the laws of nature? What do you think? Let us know what you think comes next in the comments below. And if you enjoyed this explainer on the incredible technology that shapes our world, be sure to subscribe, leave a like, and maybe share this with a friend. It really helps us keep these deep dives coming. Thanks for watching.